Hello viewers, welcome back to this course. So today we will start with the lecture 13. So in the previous lecture we have discussed the regular falsy methods, the secant method and its order of convergence. Now we will start with the another method, that is a very important method, is called the Newton-Raphson method. So like till now we have discussed the methods which is mostly based on the two initial guess. So in the Newton-Raphson method, how it works is that, so suppose I have a equation f(x) equal to 0 and I want to approximate its root. So let alpha is the exact root. So in this case what do you do? So for example, let this is my x and this is my f(x), and so that is my suppose function, so that is my f(x). Now in this case what I do is that I will start with the point, and that point I call it x0. So at x0 I take the tangent line and I will see that where this tangent line is cutting the x-axis. So wherever it is cutting the x-axis I call it x1. So now after getting the x1, so this is the point, I will take the tangent line at this point and I will see that where it cuts the x-axis and I will call it x2. Now at x2 I will get the value of this function and then at this function I take the tangent and that I will get x3, and based on this one that is the point of the root, and so with the as the iteration grows or moves on, then our iteration point or x1, x2, x3, you can see that they are heading toward the root of the equation. So that is the concept behind the Newton-Raphson method. So how it works? So I start with the initial guess, initial approximation, that is my x0. So based on this one I will get my f of x0. Then I will write the equation of the tangent at x equal to x naught. So this is equal to y minus y naught is equal to f dash at x naught x minus x naught. So that is the equation I can take as a equation number 1. So now I want to see that where it intersect the x-axis. So putting y equal to 0, because intersecting the x-axis. So intersecting that x-axis, it will get the y equal to 0. So putting at y equal to 0, I will get minus y naught is equal to f dash x naught x minus x naught. So based on this one I can get my x is equal to x naught minus y naught over f dash x naught, or from here I can write my x naught minus y is what, f at x naught and f dash x naught. So based on this one I will get my x is equal to x naught minus f of x naught by f dash x naught, and I will calling it x1, so that will become my x1. So based on this one I can make this process the iterative process, and from here I can write that xn plus 1 will be equal to xn minus f of xn divided by f dash xn, and n can be started from 1, 2, 3 and so on. So this is the iterative process and this is called the Newton-Raphson methods, NR method. Okay. So, based on this one I give the value of the function and its derivative, and then based on the iteration I will do my approximation for the given root. So, that is the iterative methods, iterations for the Newton-Raphson method. Now, based on this one I can see that this method can be written as x n plus 1 is equal to phi of x n, where my phi of x n is x n minus f of x n divided by f dash x n. So, based on this one I can say that this method is similar to the my iterative method, fixed point methods. So, based on this my fixed point method I can write this as x is equal to x minus f of x divided by f of x. So, that is my phi of x. Now, I know that for the convergence of the methods that we have discussed for the fixed point methods, the necessary and the sufficient condition was that the phi dash alpha modulus value should be less than 1. So, based on this one I just try to find what is the value of phi x. So, if I put the value of the phi x, it will be 1 minus f dash square, then f dash square minus f double dash, and based on this one it will be f dash square minus f dash square plus f double dash divided by f dash square. So, this will cancel out. From here I can say that phi dash x is equal to f double dash by f dash square. So, that is the condition we got. So, based on this one, for the necessary and the sufficient condition for the convergence, of the Newton-Raphson method, my f at alpha, f dash alpha by f dash alpha square modulus value should be less than 1. So, that is my necessary and the sufficient condition for the convergence of the Newton-Raphson method. So, in this case also we do not know generally we do not know what is the value of alpha. So, we will start the process with f of x 0, f dash double dash at x 0 and f dash x 0 square less than 1. So, in this case you can see that the numerator has f and f double dash, but denominator has a f dash. So, in this case it may happen that the value of f dash at x naught is very small. So, in that case this value will be always greater than 1. So, we have to take that function or the value of the function such that my f dash x naught is not too small. So, that is the also one of the condition. And how it possible? So, from here I can say that in the initial lecture I told you about the simple root and the multiple root. So, it may happen that f x equal to 0 has multiple root at x equal to alpha. So, in that case f dash alpha is also 0. So, what will happen in that case? My f is also 0. So, in this case my f alpha is 0, my f dash alpha is 0, and suppose I start with the initial f x naught and that is very small, f dash x naught that is also very small. So, in that case this condition may violate. So, this method is not good to find the roots for the which is of the multiple type. So, Newton-Raphson method is good to find simple root. For the multiple root we have to make some change in the Newton-Raphson method. So, this Newton-Raphson method is good to find the simple root. Okay. Now, let us find out its order of convergence also. So, let us write down the order of convergence. So, order of convergence or rate of convergence. So, in this case I have the equation x n plus 1 is equal to x n minus f of x n divided by f dash x n, and n is starting from 0, 1, 2 and so on. Then I know that I can write this equation as alpha minus E n plus 1, that is the error introduced at the n plus 1 step, and this is equal to alpha minus E n minus f of alpha minus E n divided by f dash alpha minus E n. So, this alpha will cancel out, and from here I can write my E n plus 1 is equal to, so this minus sign is there, minus sign is there, and this minus sign will cancel out. So, it can be written as E n plus f of alpha minus E n over f dash alpha minus E n. So, from here I can write E n plus 1 is equal to E n f dash alpha minus E n plus f alpha minus E n divided by the whole f alpha minus E n. So, this can be written as. Now, I will go the same way. So, from here I can expand this one with the Taylor expansion. So, based on this one I can write my E n and then f dash alpha minus E n f double dash alpha plus E n square by 2 factorial f triple dash alpha and so on plus, so this E n is multiplied by this only, plus f of alpha minus E n f dash alpha plus E n square by 2 factorial f double dash alpha and so on. And then I will divide this by the same f dash alpha minus E n f double dash alpha by 2 factorial f triple dash alpha and so on. So, that is my condition here. So, based on this one, this f alpha I know that this value is equal to 0 because that is the root. So, f alpha is 0, and from here I can write E n f dash alpha minus E n f dash alpha, this will also cancel out with this. So, from here I will get, I can write this as minus E n square f double dash alpha plus E n cube by 3 factorial f triple dash alpha, and I can ignore all the terms after that because then it will be E n raised to power 4. So, I will ignore all the power of that plus, so this is cancelled out. So, it is E n square by 2 factorial f double dash alpha, and next is I can write E n cube by 3 factorial f triple dash alpha, and I can ignore all the terms after that. And here, so this one is f alpha. So, in this case also I can ignore the higher power of this. So, I will keep only f dash alpha minus E n f double dash alpha plus E n square by 2 factorial f triple dash alpha, and I can ignore all the terms. So, from here I will get, so this is alpha. So, from here I can write minus En square by 2, because this and this, so it is minus 1 plus half, so minus half, so it will get f dash alpha, this term will get plus, I can calculate from here. So, this is a basically 2 factorial. Okay. So, that En will multiply En cube by 2 factorial. So, f triple alpha, and here it is minus En square plus next is En cube by 3 factorial and so on. So, this one I can have En cube by 2 factorial minus En cube by 3 factorial f triple dash alpha divided by f dash alpha, I just take common. So, I will get 1 minus En f double dash alpha by f dash alpha plus En square by 2 factorial f triple dash alpha by f dash alpha. So, this will can be written as, now what I do is that I will take En square by 2 f double dash alpha from the numerator and f dash alpha from the denominator. I take this as a common. Okay. So, if I take this common, what I will get? Now, maybe these terms, if I ignore the cubic power of n, ignoring the En cube or En minus 1 cube and all other higher order term. So, in that case this will also cancel, this will be ignored. So, from here I will get 1 minus En f double dash alpha over f dash alpha plus En square by 2 factorial f triple dash alpha over f dash alpha minus 1. So, I have written this form, and based on this form, so now it will be minus sign. So, I can from here I can take this term as a common and putting this minus sign here. So, I can write from here that minus En square I can write from here minus f double dash alpha over 2 f dash alpha En square. So, this one I can write, and I can write from here 1 plus En f double dash alpha over f dash alpha minus En square by 2 factorial f triple dash alpha, this one. Now, if I multiply these terms inside, then this will be a cubic, this will be a 4 power. So, from here I will get only one term, that is f double dash alpha by 2 f dash alpha En square. So, this can be written as En plus 1, ignoring all the terms. So, based on this one I can write my En plus 1 is equal to sum C En square, where my C I can write as f dash alpha to f dash alpha. So, that is the positive, the absolute value we take. So, based on this one I can write that this Newton-Raphson method can be written in this form, and from here I can say that the Newton-Raphson method is a second order. Is a second order method. or we can say that in this case my p is 2. So, based on this p I can say that this method is much faster than fixed point method and regular falsi. So, based on this one I can say that okay, I should get much faster convergence when I apply the Newton-Raphson as compared to the fixed point methods or the regular falsi method. But based on this one we can also see that if we want to be sure that our convergence, the Newton-Raphson method should converge, then we have to apply this condition also, that if this condition is satisfied, only then my Newton-Raphson method will converge, and if it is converged, then definitely it will be of the faster order. So, based on this one I can say, so the method will converge faster if C is smaller, because as small the C is, the error will be reduced in the next step and the method will be much faster. So, error will be, C will be smaller, then this value will be smaller. So, in this case also we are my C is dependent upon the f dash alpha. So, my f dash alpha should not be small, because if my f dash alpha will be small, then the C will be level very large, and even in that case my the condition, sufficient condition for convergence is not satisfied. So, in that case my method, Newton-Raphson method may not converge, and if it is suppose it converges, then the rate of convergence is not much faster, because the C will be very large. So, in both the cases we have to rely upon the f dash alpha. So, this is all about the Newton-Raphson method. Now, we have discussed the various methods. So, let us see that how we can find out the order of convergence when we are dealing with the codes. So, this is how to find convergence rate numerically. Like we have made the, suppose we make the code for Newton-Raphson for the fixed point, for the regular falsi. See, in all the cases we will want to see that how the rate of how we can find the rate of convergence numerically. So, how we will do that? We know that my En is equal to C E n minus 1 p, that is the definition of the rate of convergence. Similarly, I can find my En plus 1 is equal to C E n p. So, based on this one I can find my En over En minus 1 p, that is equal to C, and based on this I can write En plus 1 over C. So, from here I can write my En is equal to En minus 1 p is equal to En plus 1 is equal to En p. Now, from here I can write my, so this can be written as En p plus 1 can be written as En plus 1 into En minus 1 p. So, based on this one, or maybe I can write like this, because this will not going to serve any purpose. I can write from here En plus 1 is equal to En, that is equal to En over En minus 1 power p. So, from here I can write, then I take the log both side. So, I can take the natural log. So, based on this one I can write P is equal to log En over En minus 1. Okay. So, based on this one, my P can be written as log of En plus 1 over En divided by log of En by En minus 1. So, that gives me the order of convergence. So, to find the order of convergence, what should we need? We should have the value of En minus 1, En and En plus 1. So, I suppose I have a 3 point. So, that is the error I am getting at the En minus 1 step, then at En and then En plus 1. So, at the 3 points, if I know the error, then based on this error I can find the value of P. But now the question is that suppose I take the Newton-Raphson method, and then if I see that starting from the initial point x0, x1, x2, x3, x4, I will get the error E1, E0, E1, E2, E3, E4. So, if I put this value, should I get the value of P always 2 in the case of Newton-Raphson? So, that is not the case, because as we start growing the iteration, and we know that our method is converging to the root. So, as we grow with the iterations, so after some iteration you will see that for large P, for large n, the number of iteration, so I can say that my xn will grow. So, in that case I know that limit n tends to infinity, my xn will converge to alpha. So, in that case I can say that limit n tends to infinity with this value log En plus 1 over En divided by log En minus 1, that will converge to P. So, it is not going to give you the value always the same value of P, but for the large value of n, or we can say that this converge to P in the limit n tends to infinity. So, that is the way we can find the order of convergence numerically. Okay. So, that is the end of this lecture. So, in this today lecture we have discussed the Newton-Raphson method, its condition, necessary and sufficient condition for the convergence, and then we have discussed its order of convergence, and that is the second order method. So, in the next lecture we will do some MATLAB coding to find that, to try to write the codes for Newton-Raphson, for fixed point, for regular falsi, and then we will see that whether whatever the order of convergence we are getting theoretically, that matches with the numerically or not. So, that we will done in the next lecture. Thanks very much. Thank you.